We're going to have a go at drawing some adjacency matrices for some different networks. Now this one's got 7 points, so we're going to have to draw a 7 by 7 matrix. I'm going to put some row and column headings here to help us. Up to G, and down the side to G. It's going to fit on. Okay, they're just row and column headings, help us be organised. Now what we have to do is we have to indicate which of the different vertices are connected by an edge. So let's take the ones from A, we take this as being sort of from to these. Now from A there are edges that go to D, E and G. So I'll indicate those as one in each case. There's one edge from A to D, one edge from A to E, and one edge from A to G. Now A is not connected to any others, so I'll just put zeros in at other places in that matrix. The one indicates there is one edge between A and a particular other vertex. What about the edges from B? Now this is a little bit tricky here, and there are a couple of different schools of thought amongst mathematicians, and there's a couple of ways you can do this, in particular with this one here at B, where B is connected to itself. Now, what will we say? Certainly, B is connected to E and G, so we'll put a connection from B to E and one to G as well. B is connected to itself, and I'm going to indicate that with two. There's two connections from B to itself. Now there's a good reason for that, and I'll explain it at the end of this little session. Let's get our matrix together first, and then we'll talk about that. Now B is not connected to any of the others, so we can put zeros in for the rest of that row. What about C? Well, C is connected to D, and it's also connected to F. So from C to D there is a connection. C to F there is a connection, none others. I think you can see how this goes. From D there are connections to A, to C, to F, and to E. The other vertices are not connected to D. E is connected to A, to D, and to B. F is connected to C, to D, and to G. And finally, G is connected to A, B, and F, and none others. We've completed our adjacency matrix. Now, a couple of things to notice. A matrix like this, if it's an undirected network, as opposed to the directed one over here, with an undirected one there's a symmetry to it. It's symmetrical around this main diagonal down here. So elements over here, this one and one here, match this one and one here. It's almost as if you could fold it over diagonally, it would match up. If you look at this row here for A, we're saying that A is connected to D, E and G, if you look at the connections from A, but if you look at the connections to A, by looking at this column here, it's exactly the same. A is connected to D, E and G. That row 0, 0, 1, 1, 0, 1 matches this column 0, 0, 0, 1, 1, 0, 1. And it's the same throughout that matrix because there's no direction to it. Coming back to this entry here of 2, one of the reasons why I prefer to put the 2 there, some mathematicians would put a 1 there, Well, the reason I prefer it though is this: if you look at the row totals, the total of this row is 3 for A, and that is the order of that vertex A. It tells you the number of edges which are leading to and from it. Now if we look at row B, that would say the total of that row is 4, and that tells you the number of edges leading to and from B. It's consistent with our idea of the order of a vertex. Okay, let's move over and do the next one, which is a directed network. Once again, it goes up to G, so we're going to have to draw ourselves a 7 by 7 matrix. I'm still fitting on the video just. Okay, so now we've got to be very careful with our from and to. So from A, there are vertexes which lead to D and F. So from A to D and F, otherwise none. From B, can you see that all of the arrows lead inwards? So from B, there is none to any vertex. From C, you can get to E and G by just one route each, others zeros. From D, you can get to B and F, but not to A or E because the arrow is going the wrong way. So from D, it's B and F, others are zeros. From E, you can get to B and D, but not the others. B and D, okay, not the others. From F, you can get to G and B, not others. And from G, you can get to B and E, not others. And so there we have our adjacency matrix. A little extra question you asked there to identify a source and a sink for this directed network. Now a source is a vertex from which things flow out of. All of the edges there will be leading out of a source. Now you can see it just on the graph. You can see there are two edges here that from A, two edges lead out, nothing leads in, so that must be a source. Similarly C, we've got edges going out, nothing goes in, it's a source. But how's that shown on the matrix? Well, on the matrix you can see there's a whole column here of zeros for A. Whereas if you look at row A, it's got a couple of ones in it. Then those couple of ones there indicate things are flowing out of A, but this here says that nothing is coming in to A. So that indicates, that column of zeros in particular, indicates that A is a source. Similarly, column C, for the column for C, is showing a whole column of zeros. So nothing is flowing in to C, whereas row C, we've got stuff flowing out. So A and C are sources because they've got vertices leading out but not leading in. Now you can see here that vertex B has got, so from the graph, everything's leading in to B. So B is a sink, and you can tell from the graph. But what about on here? Well, if we look at what's connecting to it by looking at the row for B. We can see a row of zeros. That means that nothing is coming from B, whereas we've got things flowing to B. If nothing's coming from it and we've got things flowing to it, then B must be a sink. So A and C are sources. B is a sink.